Okay, so for the following circuit here, we have to find all of the following here. So we're told that this switch is closed when t is equal to 0. So let's draw the circuit when t was less than 0. So this will be open, so we can just pretty much ignore all of this. Okay, so we have the circuit when t was less than 0. And for this inductor, its voltage is pretty much the inductance value times the change in current over the change in time. And we're going to make this assumption that the switch over here, it's been open for a pretty long time. So we're going to take this to be infinity, or dt to be infinity. So that means this is all just 0. And we can replace this with a closed wire. And for the current passing through this capacitor, it's going to be the capacitance and the change in voltage over the change in time. And the same principle, we're going to take this to be infinity. So it'll be an open wire here. So that means there's no current passing through it. Now, what we're trying to first find is find I at 0 and V at 0. To find I of 0, it's going to be pretty easy. It's going to be 12 equals I times 10 plus 2. So I will just be 1 amp. Okay? So this is, it's 1 amp when t is less than 0, but the second t is equal to 0, I is not going to change instantaneously. So I will still be 1 when t is equal to 0. So we're going to put that here. Okay? So I at 0 is going to be 1 amp. Now, for the voltage here, we see as we travel through here, there will be a voltage drop here. So it'll be 12 minus 10 times I, which is 1. So it will be 2. So the voltage here will be 2 volts, and that will be the voltage here. And it's the same principle. So like it's going to be 2. This is going to be 2 volts when t is less than 0, and the second t is equal to 0 when we close this switch. This is not going to change abruptly. So V at 0 plus is going to be 2 volts. Okay, so that's all done. Now let's draw the circuit when t is equal to 0. So when t is equal to 0, we have the following circuit. Hold on, let me draw this more bigger. Okay, so first thing we see is this resistor is pretty much useless because all the current will be traveling through this wire. Okay, it's going to be traveling through this wire because this wire has no resistors. So they're going to all avoid this one. So we can just rewrite the circuit like this, or we can just draw it like this way instead. Let's do it like that. Okay, so we have a current passing through here, and obviously this current is 1 amp. We know the voltage at this region. It's going to be 2 volts. So pretty much what we're trying to right now find is di at 0, di over dt when t is 0, and dv over dt when t is 0. So so if you recall, the formula for voltage at a inductor is equal to the voltage times the inductance value times the change in current over the change in time. So if you rearrange these, we just have to find the voltage when t is 0 at the inductor. And for the capacitor, and for this one, we see it's current equals the capacitance times the change in voltage over the change in time. We arrange these. We just have to find the current when sorry, we have to find the current passing through the capacitor when t is equal to 0. Okay, so let's focus on this one. To find the voltage at our inductor here, it's going to be pretty much going to be the voltage, the difference of voltage here and here. All right, so we know the voltage here should be 2 volts, and the voltage here should be 12 volts. So 12 minus 2, that's just 10 volts. So the voltage at this inductor is going to be 10 volts all over the inductance value, which is 0.4. And let me see what that gives me. That gives me 25, and this is in amps per second. Okay, so I'll just write that here. And the reason it's amps per second is I is in amps and T is in seconds, so amps per second. There we go. Now, so for this one, let me just erase all of this. Recall that when T was less than 0, the current passing through this capacitor was 0 amps. And obviously that's not going to change instantaneously when we close the switch. So that means the current currently passing through this capacitor when T is equal to 0 is going to be 0. So that means all of this is just 0. So we have dV at 0 plus over dt equals 0 amps. Now let's solve the last two, which is finding I at infinity and V at infinity. So I'll just erase all of this. Well, actually, I shouldn't. Actually, we could just work with this one because when we go to hold on. Okay, so pretty much let's put our attention to the inductor and our capacitor. When t is greater than when t goes to infinity, pretty much what happens is recall the formula for the current passing through here is equal to the capacitance and the change in voltage over the change in time. So that means obviously we can just ignore this and replace this with an open wire. And this, the voltage at our inductor is equal to the inductance value times the change in current over the change in time. So obviously we can just replace this with the closed wire. So we have a new circuit like this. There we go. Oh, hold on. There we go. Okay. So what we have to do is find the current passing through here, and the current passing through here will be 12 volts all over 2 ohms. See? So this will be the current. This will be this I value, and that gives you 6 amps. So and that's going to be your I of infinity. And your voltage, which is the voltage here, will literally just be 12 amps because the voltage of this whole node is going to be 12. Sorry, not 12 amps, 12 volts. So it'll be V infinity equals 12 volts.